Here we're going to start talking about decision analysis, and this is chapter 13 in your book if you're following along. The example that we're going to work through is this company PDC, and we want to analyze their decision making. So PDC is considering 3 different project sizes for their new condo complex. They can either do a small complex with 30 condos, a medium complex with 60, or a large complex with 90 condos. They need to decide which project they're going to do in order to maximize profit. But the problem is they don't know what the demand's going to be. So it's possible that they could build a small condo complex, but then the demand would be 70, and that would have been a mistake on their part because they're missing out on a lot of profit. Or they could, choose a large condo complex, but the demand could only be 40, so then they have 50 condos that are just going to be empty. So they don't know the demand, but they need to decide which complex they're going to build. So their decision alternatives, they're going to have 3 of them. They could either go with D1, which we'll call the small complex. They could go with D2, which is the medium complex, or they could go with D3, which is the large. So we need to decide which one of these is going to be the solution. And we'll look at a couple different ways to analyze this, but in the end, each time, the answer is either going to be D1, D2, or D3. But they also have chance events, and those are the demands. So we don't know what the demand for these condos is going to be. So we'll have 2 states of nature. We'll have S1, which is going to be a strong demand. And then the other state would be S2, which is a weak demand. And these 2 are unknown. We don't know if the market is going to call for a lot of people demanding a condo or not a lot of people demanding a condo. So we're just going to label those S1 and S2. And those are the chance events. We don't know what they are, but we'll call them the states of nature. What we do know, though, is that if you know the state of nature, the S1 or S2, we know the payoff for each decision. So in this first row, let's say that they decide to build this small complex and we have a strong state of nature. Well, then the payoff is going to be 8. And these are in thousands, right? So these are going to be 8,000 per whatever our time unit is. If we have a weak state of nature, then our payoff is going to be 7 if this company chose to build the small complex. And you can read the rest of this. So if they built the medium complex and we have a high need for condos, then you're going to get 14 for the payoff and then 5 for the payoff. And then if you build the large complex, we'll have 20 and -9. So you can see that if they build the large complex, so D3, but then they have a weak state of demand, you're going to actually be losing money. So we also can make a decision tree on this. So if you're more into pictures instead of charts, that's fine. So in the decision tree, they need to decide if they're going to choose D1, D2, or D3. And this is your payoff for the decision tree. Based on this, each one of those decisions will have a state associated with it. So for D1, if you're in state 1, so our strong demand, that would be 8. If you're in state 2, you'll get 7. For this one, would be 14, then 5, and 20, and -9. And maybe this is a little bit easier to read. I mean, it just really depends on how you like to see things, but you can kind of see all these branches. So let's say that the company in blue here, the company decides to build the medium complex, and then we have a strong demand. Well, then my payoff is 14. Or I can draw another one here, maybe in purple. Let's say that the company decides to do the large complex, but then we have a strong demand, their payoff will be 20. So this is kind of the payoff table. You can see it in terms of the tree, but this table we're going to use for all the different approaches that we'll look at. first approach that this company could use in deciding which one to build is called the optimistic approach. And in the optimistic approach, all you do is you choose the largest profit. So in the optimistic approach, you assume that things are going to go well. It's optimistic. So you just look at what is the highest profit in this table. So in this table, the highest profit is 20. And that was given to us by building the large condo. So if we're using the optimistic approach, the company should build the large condo complex. So D3 would be our answer. We also have the conservative approach. So for the conservative approach, what you want to do is look at the minimum profit for each decision, then choose the largest one. So you want to look at the minimum profit for each, I'll call it D sub I, so each of your decisions, and then choose the max of those. That's called the conservative approach. So let's look at our first decision. What is the minimum of that? So I'm kind of making a little table here. So for D1, it looks like the minimum was 7. For D2, the minimum was 5. And then for D3, the minimum was -9. Once you have that, we're going to choose the largest. Looks like the largest here is 7, which corresponds to D1. So if you're looking for a conservative approach, our answer would be to build the small complex, and then your payoff would be 7. The conservative approach kind of assumes you're going to have, it's not going to go as well as it would in the optimistic approach. So we're just looking at the minimum of all the payoffs for each decision and then choosing the largest from those. The next one that we have is probably the most complicated one. It's called the minimax regret. So minimax regret. And what we want to do for this one is we want to minimize the maximum state of regret. The idea with this is that, you don't want to have a strong demand and then have built the small complex. You would have a lot of regret over that. But at the same time, you don't want to build the large complex and then have low demand. There would be a lot of regret there. So we're trying to minimize the maximum state of regret. And the way that we're going to do that is we are going to use the formula R sub ij, this is going to be our regret, is the absolute value of V sub j star minus V sub I j. And what these are, so I is the regret with decision I and state j. V sub j is the payoff corresponding to the best decision for j, for state j. And then this last one is the payoff with decision j, sorry, I, not j, and state j. So those are your 3 variables. You can see they're kind of a lot. What we're going to need to do is we're going to need to figure out all of these regrets, and then we're going to find the smallest of them. So we need to figure out R11, so that would be the regret of building a small condo and then having high demand. We're going to need to figure out R12, so that's the regret of building a small condo and having weak demand. We're going to need R21, so that's building medium, having strong demand. R22, so that's building medium, having weak demand. We need R31, So that's building the large complex and then having strong demand, and then also R32. So we need building when you build the large complex, but then have weak demand. So we're going to go through and figure out all these and then minimize the two. So let's start with D1. So D1 is going to have R11 and R12. So what this formula said, I'll write it up here in case you forgot it. So it was R sub ij was Vj star minus Vij. So R11, this says if you look in state 1, what is the profit that's corresponding to the best decision for that state? So if I'm looking for R11, I'm looking in state 1. So in this column, what's the largest profit? So that was 20. Then minus the payoff with decision I and j. So this is the payoff with decision 1, 1, which was 8. So we get 12. Next, R12. So the first part is if you're looking at S2, what is the largest profit? And largest profit was 7 minus the actual profit of choosing decision 1, state 2. Well, that would be 0. All right, now for D2, we're going to have R21, R22. So for R21, that's the maximum in state 1, which we already know was 20, minus what the payoff would be if you chose 2, 1. So that was 14. For the next one, it's going to be the maximum if you chose state 2, which was 7, minus 2, 2, which was 5. And then lastly, decision 3 is going to have 2 of these, so R31 and R32. So for this one, again, that's that maximum in state 1. And then 3, 1 was actually 20, so that's 0. And then our maximum for state 2, which was 7, minus 3, 2, which was 9. So that's going to give me 16. So this is called the mini-max way that we're going to do this. So the mini-max analyzation of this. So what we're going to do is in D1, what is the maximum? So we're minimizing the maximums. So I'm going to choose the maximums for each decision. And then of those, what's the minimum? So you're minimizing the maximums. So the minimum there is 6. So this company, if they're using this approach, the mini-max approach, they should choose D2. So that's the mini-max approach. You should go through, find all the regrets, then find the maximum of all the regrets, then choose the minimum associated with each decision. And now the last thing that we're going to do is look at decision making with probabilities. So if we maybe don't know what the state is going to be, we don't know the state of demand, but we maybe know the probability of each state of demand, then what decision should we choose? So in this example, let's assume the probability of having strong demand. So the probability of being in state 1 is 80%, so 0.8, and the probability of being in the weak demand was 0.2. And you notice they have to add up to 1 because you're either going to have a strong or weak, we don't know, but one of them has to happen. Then we can find the expected value. So for the expected value, what you want to do is you want to take the probability of S sub I and then times the probability, times the payoff associated with that, and then you're going to add them all up. So you're going to add up a bunch of things. The formula for it involves a capital sigma. I'm not sure if you're comfortable with that, so I don't want to write that out, but the expected value is take each of the probabilities times the payoff. So let's actually do these three. So if the probability of S1 is 0.8 and the probability of S2 is 0.2, let's find the expected value for decision 1. So it's going to be the probability of 0.8, so the probability of being in S1 is 0.8, times the payoff for that state, plus the probability of being in state 2 times the payoff for that state. So I got 7.8. For D2, it's going to be the probability of state 1 times the payoff for state 1, plus the probability for state 2 times the payoff for state 2, which I got 12.2. And then the last one, probability of state 1 still 0.8 times the payoff for state 1, plus probability of state 2 times the payoff for state 2, which gave me 14.2. So if you know these probabilities, then you can figure out the expected value and say, well, the expected value of D3 is 14.2, and that's the largest. So here the solution is to build the large complex. If you know the probabilities, of course you have to know the probabilities in order to do this. Before we start playing around with maybe we don't know the probabilities, let's do one more example of finding the expected value. With the expected value for D1, so it's going to be the probability of state 1 times the payoff for state 1 plus the probability for state 2 times the payoff for state 2, which that time gave me 7.7. Then for D2, the expected value on decision 2 is 0.7 times 14 plus 0.3 times that payoff of 5, which is 11.3. Then we have the 0.7 times the payoff of 20 plus 0.3 times the payoff of -9, which is 11.3. So this time, based on the expected value approach, you could build either the medium or the large because the expected value is the same. So this time they could choose D2 or D3. But just changing the probabilities just makes it completely different. Just going from 0.8 to 0.7 on that demand for a strong, but the strong state changed it to not just be D3. Now you have a choice. But the question is, let's say that you don't know the probability. You still want to answer the question, when is D1 the solution, when is D2 the solution, and when is D3 the solution? So what we're going to do is assume the probability for a strong demand is P, which means the probability for a weak demand is 1 minus P, because they have to add up to 1. Given that, now can we figure out the expected value for each one? So it's going to be a lot of algebra, but we can work through it. So for the expected value for D1, that's going to be probability of state 1 times 8, so my payoff for state 1, plus probability of state 2 times my payoff for state 2. And I'm going to expand this and simplify as much as I can. I get 8p for my first term. Then it looks like plus 7, and I am distributing the 7 here, minus 7p. I have 8p and minus 7p, which gives me one of them. So my expected value for decision 1 is the probability of a strong demand plus 7. And we're going to do this for the other two. So now let's move on to decision 2. That's going to be my probability of state 1 times 14 plus the probability of state 2 times 5. Just simplifying this, that gives me 14p. I just reverse the order. You're allowed to do that with multiplication. And then distribute your 5. So 5 minus 5p, which gives me 9p plus 5. And then lastly, we're going to figure out the expected value of D3. So that's P times the payoff for S1, and then 1 minus P times the payoff for S2. which gives me 20p, and I'm doing exactly the same thing. I'm just reversing the order on the first one and then distributing on the second part. Then it looks like a negative 9 plus 9p. Because this negative 9 was negative, it makes that 1 negative, but then the p becomes positive. So I get 29p minus 9. So those are our expected values. And what I'm going to do is I'm going to graph all of these. So I'm going to graph 3 equations. The first one, we'll call it y1, is p plus 7. The second one, which I'll call y2, is 9p plus 5. And then my last one, y3, is 29p minus 9. Remember that we're trying to maximize the expected value. So if I graph it this way, using y as the expected value and then p as my x variable, whenever one of the curves is on the top, that means that D1 should be the solution. So if this line is on top, then D1 is going to be the solution. Whenever this line is on the top, so when it's the highest, D2 will be the solution. And whenever this last one is on the top, that means that D3 is going to be my solution. So I've graphed those here for you. You'll see that the red line, I used x's instead of p's just because I want to actually be able to measure that on the x-axis. But I've graphed this for you using Desmos. So I graphed y equals x plus 7, y equals 9x plus 5, and y equals 9x minus 29. So if I'm looking at this, the red line that was associated with D1, blue was D2, and green was D3. When was the red line the highest line? Well, it looks like the red line is on top of both the blue and the green from here to here, which means the probability was between 0 and 0.25. I clicked that point so you can see the coordinates. So I know that D1 is the solution whenever P is between 0 and 0.25. If P is equal to 0.25, then you could go either red or blue. It's fine. Next, when is the blue line on the top? So when is D2 going to be the solution? For what probabilities? So if I look over here at my graph, it looks like the blue line is on the top from here, and it stops being on the top right there. And that's going from my x values or my p values from 0.25 to 0.75. And I'll put the equal to there because when it's equal to 0.25, either decision is going to result in the same expected value. And then lastly, when is D3 the solution? So when is the green line the highest? But it looks like it starts here and then continues to be the highest from there on out. But remember, probabilities are always less than or equal to 1. So we'll say from 0.75 all the way up through 1. So based on this, I can make a couple of assumptions. So let's say that you know the probability for S1. Like if the probability for S1 is, let's say, 0.6, then I don't need to do all of that calculation I did before. I can just say, oh, that's between 0.25 and 0.75, so D2 would be your best bet. Let's say that I know the probability of a strong demand is 0.9. Well, then I can say 0.9 is between 0.75 and 1, so D3 is your solution. Let's say that we know that the probability of a strong demand is 0.1. Well, 0.1 is between 0 and 0.25, so that would mean that D1 is my solution. So we can take just a general probability, that P, and we can kind of manipulate everything to say, when is D1 the solution? When is D2 the solution? When is D3 the solution? And now we have those values.